All right. Here's what I want you guys to consider for this one. If we take an object and we apply a torque to it, we're going to be causing it to move. And if we do that, if we move the torque over an angular distance, then we're obviously changing its kinetic energy as we do that. So, so we have to have done work in some case. So what we're going to look at is the work energy and power for rotational motion. All right, and this is of course the work energy theorem. So we're going to start with if W net. Okay, if we do if there's a work done by a net force, that is going to give us our change in kinetic energy. Well, and so where do we go with this? And we get our integral of our force times our displacement, and this winds up giving us 1/2 mv final squared minus 1/2 mv initial squared, right? Okay, but then we're going to take, if we go with this and we do our analogous variables, we're just going to throw stuff in. They're just going to throw our analogous variables. This isn't a proof. This is just saying, hey, this will, believe it or not, this actually works. So we continue this, and we're going to get the integral then. So what's our analogous variable for force then is going to be torque. Okay, is going, times, and what's going to be our displacement analogy for r? Well, it's going to be theta, right? So r d theta, okay, is going to equal, and then we have these guys over here. So we have a mass and we have a velocity, and we have a mass and a velocity. Well, we're going to have 1/2. That's the constant. 1/2 is 1/2. Our rotational analogy for mass, though, is our moment of inertia. Okay, and our rotational analogy for velocity is omega. It's angular velocity. So we're going to have I omega final squared minus 1/2 I omega initial squared. And this becomes our rotational analogy for our work energy theorem. Sorry, guys, I need to deal with something here. All right. So now, now we're going to take an object and we're really going to examine how this works. So we have an object and it is spinning in a circle. Okay, and we're adding a bit of perspective to this. We're kind of looking at it from an angle. And then we have a mass over here. All right, and from the center of our circle, we have our radius that points to our mass. That's our r. And we're going to apply a force to this, and this has a tangential force. That's going off in that direction. Now, this object will travel along this arc length right here, and we're going to call this arc. What do we call our arc length? Let me reset up a little bit. Okay, our arc length is we call our arc length S. So that's going to be our delta S. And if it travels from along that delta S to a new R, we have an R initial and an R final. All right, if we have our R initial and R final, and we travel along a delta S, then what we're really doing is that if we're forcing along this delta T, then what we're really getting is the force, and this is our force, our tangential force. Then we get F of T times our delta S, which is the arc length, is going to equal our 1/2 m v final squared minus 1/2 m v initial squared. But we know that v equals r omega, and we also know that our delta S, if we divide it by the length of the radius itself, that we get that equals a delta theta. Okay, or change, or another way of writing this is that delta S equals r delta theta. So we take this and we can rewrite it as our tangential force times our delta S is going to equal 1/2 of our mass times r omega final squared minus 1/2 times our mass times r omega initial squared. And this is our, these are still our energies. It's our change in energy. Well, then we go from there, and we can rewrite this to get 1/2 mr squared omega final squared, and we can group this together, minus our 1/2 mr squared omega squared. Okay, but then what do we have here? For any particular particle, this is our mr squared and our mr squared. Well, that would be the moment of inertia of any one particular particle. And so from this we get our 1/2 I omega final squared minus our 1/2 I omega initial squared. And there you have it. That is our work energy theorem. However, we take a look back over here, and we need to convert this back into rotational also. And so what is really our force? Well, we know that if this is force times delta S, we figured out the delta S over here was r delta theta. And so we can rewrite this portion as our tangential force. Again, delta S can become r delta theta, and what is this? This r times F becomes tau delta theta equals 1/2 I omega final squared minus 1/2 I omega initial squared. And there is our work energy theorem, completely in rotational inertia, or rotational variables, which is what what we're looking for, and that's how we derive it. And that's without just the analogous variables, without just saying, well, hey, it works. But if at this point we let delta theta approach 0, then we can take the limit of it, and you've seen where this happens before. Whenever we have a delta, we really get that the integral of tau d theta equals 1/2 I omega final squared minus 1/2 I omega initial squared. And that is truly that winds up being our true work energy theorem for that. Okay, now we can extend this into power. So we're going to move over here a little bit. And power, all right, where power is going to equal dw. Now, to be sure that this is not omega, and I will tend to write work. I sometimes write work with a rounded points down here, so I'll try to make sure that I'm not doing that when I'm dealing with power. Power equals the change is our dw dt, or change in our work over time. It's the rate at which we are doing our work. But we've now found a new version of work. Our work is okay. We operate on our work as the time derivative of the integral of tau d theta. Well, for most intents and purposes, our tau is going to be constant. So we're going to assume right now that our force isn't changing over time, although it could. And then we're going to get this is really equal to, the power equals to our torque times, well, if we take our time derivative of d theta, then we actually get instead of just d theta, we get a d omega, where the time derivative of d theta is d theta dt, and that becomes tau of dw. Okay, and so power, okay, for a certain amount of velocity, and the force that is being applied is tau omega, okay, or which is, you know, the same thing as force times velocity if we're dealing with straight line stuff. Now, I'm leaving the vectors off of this intentionally because our axes are generally fixed, and if our axes are fixed, we're not actually changing the axis of rotation when we're doing our work or doing our power, then we don't need to throw in the cosine theta, because they're pretty much going to be perpendicular to each other, and that's I'm sorry, along the same lines, and that's the force is in the direction of the velocity and that sort of thing. Now, this does bring us to rolling motion, which you guys will see in your work. Okay, now what we're going to do is assume that we have an object that has a constant moment of inertia. That means the objects within it aren't fluid. You don't have an object that's distorting, you know, that as it spins along an axis, let me get those out of the way. As it spins along an axis, it distorts and gets squishy. You'll sometimes see this if you, what kind of things have that? Okay, if you have those little wet, little squishy balls, squishy sponge balls that you play within the pool, that you essentially it's a sponge wrapped in an absorbent material that you can throw, and it's like hitting somebody with a wet sponge, except you're playing in the pool. Well, if you throw it really hard and get a lot of spin on it, you'll see it elongate around its equator, and that adjusts its that changes its angular momentum. It changes its angular moment of inertia, and that, you know, so it starts spinning it with a different rate. And so that's not what's happening here. This time we're just assuming that I is constant. And so what happens is we have a bowling ball. Okay, here's a bowling ball, and it's going to be a pretty bowling ball. And it's going to be roll down. It's got a radius. Okay, it is traveling with a certain velocity. Okay, and it has a particular mass. We will call m. Okay, it is a mass of bowling ball of mass m rolling down the lane. Now, because it is rolling, not only is it going to be moving with a certain velocity, but it is also going to have an omega. Okay, it's going to be rotating as well. And so, the rolling motion, now when we say rolling, rolling has a very particular, this has a very particular meaning to it. Rolling motion means that at this point right here, there is no sliding going on. That at the point of contact, that they are, the relative motion of the point of, the relative motion of the points of contact of the ball and the floor is 0, that they are touching each other and there is no sliding, that's when something is rolling. This is a very important concept here, because otherwise it would be sliding down the floor. Now you'll see bowling, now not all bowling balls do this, they take care of the ball in certain ways. And they take care of the lanes and the balls in certain ways that allow for a predictable amount of slide when you're bowling. That is, you're going to slide down the rail, and so you put a certain amount of spin on the ball, and then you get it slides down the lane, and then it catches all of a sudden. Then you see the bowling ball curve. If you watch, I'm not recommending that you do this aside from just the physics of it, but if you watch professional bowlers, when they're bowling during the NFL season, because that's what's on ESPN during the morning when NFL is playing, you'll see the ball slide down the lane, and then all of a sudden the spin catches, and the ball's attacks the bowling ball attacks the pins at a different angle. But what we actually have here is two different kinds of kinetic energy. The ball is moving down the lane with a mass and a velocity. However, there's also a rotating portion to our kinetic energy. And so our K is going to have two parts. It is going to be not just the traditional 1/2 mv squared, but it is also going to have the 1/2 I omega squared of the rolling of the rolling bowling ball. Now, all objects in space will have some sort of combination of these two, particularly if it's in a gravitational field and it's a satellite. Imagine a satellite going around the Earth. Not only is it traveling very fast to stay in orbit, it is also usually spinning on its own axis to keep it pointed towards to keep it pointed towards the center of the Earth, and that allows that allows for geosynchronous satellites to point down to the same place on the Earth all the time is by its by maintaining the spin. So what's going to happen here? Well, we know that we need some way of relating our velocity and our angular velocity, and we know that velocity equals r omega, or we can rewrite this as omega equals velocity over our radius, and that's going to be important when we start relating these to each other, because our k is then going to equal 1/2 mv squared plus, now I can look this up. That's why we have these tables. I'm not going to expect you to calculate the angular velocity for a solid sphere. Okay, but I will tell you that it is that I, for a sphere, solid is 2/5 m r squared. Well, that means that this is going to become 1/2 times 2/5 times the mass times the radius of this thing squared times its angular velocity. Well, its angular velocity is going to be the velocity squared over its radius squared. And here's the wonderful thing, that this in fact, that's also squared right here, is that these radii are going to cancel. And so what does this become? This becomes a 1/2 mv squared plus a 1/5 mv squared. And now we just add the two fractions together. And this becomes, what is it? It's going to be 5 and 2. It's going to be 7/10 mv squared would be the kinetic energy of our bowling ball rolling down the aisle. Okay, I always thought that's pretty cool. Okay, however, remember that this V is usually less than, or this energy, this amount of kinetic energy, is usually, this being the kinetic energy, if all of the energy that you throw, that's used to roll the ball down, some of it's going to get lost to friction, but a lot of this is going to get turned into, a lot of your straight line velocity that you had is going to get turned into angular velocity. And the ball will actually slow down as it spins in order to get, so some of this, in order to turn some of the linear velocity into rotational. So that's pretty much it for work, energy, and power. And we'll see you guys. There should be enough to get you guys going on your homework. Bye.